Hi, I'm Rui Pereira da Costa, organizer of this International Leno Masters 2015. Today, we are closing with a golden key, or should I say, with a golden instrument. Thank you for keeping with us and for following this high-intensity endo program. I'm sure you have learned a lot already, and we are not even halfway. Today's last lecture is from my friend from France, Wilhelm Pertot. Willy did his master and PhD in endodontics in Marseille, France, and he has been teaching endodontics at Marseille School of Medicine since 1991. He has been working, among others, in the research of physical properties of endodontic instruments. Willy made the suggestion of presenting here in this Endo Masters for the very first time in the world the newest file system from Wave.One, Wave.One Gold. It will be an excellent opportunity to learn what the most advanced technology and science in endodontic instruments can bring us today and how it can transform this phase of the endodontic treatment in a more secure, predictable and efficient procedure. Willy Pertot is part of the team that developed the Wave.One Gold instruments, so I guess he's the perfect speaker to bring us all the details of this innovative system. I know this has been one of the most awaited lectures, so it is with great honor that I'll leave you with my friend Willy Pertot. We'll be back tomorrow with loads of endo content. Don't forget to use the comments area to give your feedback on this presentation or to send any questions you'd like. See you soon.
Well, hi to all of you. It's a pleasure to have you here and thank you for joining in. I want to thank also Rui for the invitation. It's an honor for me to be here with you and speak on this Endo Masters. Let me give you a glimpse about how this happened and about how lucky I feel and how lucky probably you should feel. Is that first Rui told me to discuss and speak about Wave.One, and at the same time he told me it was going to be in December and then that it was going to be in March 2015 for the diffusion on internet. And at the same time, let me tell you, we have been working for the past 2.5 years to make Wave.One evolve into a new file, which is going to be Wave.One Gold. And Wave.One Gold is meant to be launched on the market and in March, during the ADS, March 2015 in Germany. So basically, this will happen at the same time that this conference, this lecture will be online. So if you join in and you're here, you'll be among the first people to know about this new evolution and about this new file. Okay, so let's get started. Very briefly, with a brief history about files, very quickly, just to know how we got there. Remember that in 1960 we had the introduction of the first ISO files. The ISO standards that were set in 1960. Not that before we didn't have files, we had files, but they were not standardized. Then from 1960 up to 1996, we were used to use the stainless steel files with a small taper in an up and down motion. And then in 1996, we had the introduction of the first nickel titanium rotary files. That was Profile at that time. At the same time, we had the introduction of the Quantec file by a company called Tycom at that time. And it was acquired then later by Cybern Endo. And also a few months later, we had the introduction in France of Hero 642 by Micromiga. And then we had some evolutions of the file. The most important evolution in 2000, in my opinion, was the introduction of the Pro Taper. And it is important because we had the introduction of the first file on the market with a variable taper. Then we had to wait until 2011 to have really what I consider as some kind of a revolution in nickel titanium. Not only because we have modified the files and the alloys, but also because what we did is we had a change in the kinetics of the file and the dynamic of the file. And instead of having rotary file, now we have a new, safer movement, which is reciprocation. And I will elaborate on this in a few minutes. We also have, it's not because we have reciprocation that we shouldn't have rotation. Some people feel okay with the rotation, and we have also introduction on the market in 2013 of Pro Taper Next by MyFair. You know that in 2011 we had the introduction of reciprocation single file technique, These files were used in this clockwise or counterclockwise clockwise movement, and we had two files, the Wave.One system and the reciproc system, Wave.One by MyFair, reciproc by VDW. And well, let me tell you that in 2015, as I told you a minute before, we will have the introduction of Wave.One Gold, which is an evolution of Wave.One. And I'll also elaborate and show you at the end what the evolution is and how interesting these files are for our everyday practice. Very quickly, if we continue in this history, why did we go to rotary nickel titanium? Why did we modify the files? Why did we have always this need to move from one file to another, from one technique to another? Well, we have identified a long time ago all these problems related to shaping a file or shaping a canal with stainless steel file going up and down. Well, remember that the most important thing is not the alloy. The alloy is part of the problem, but the most important thing is the dynamic of a file into a canal. I mean by that is the way we shape the canals. When we were taught to take our files and push them one after the other to length, and then we used to take these small taper files and take the tenth of length and then file the canal in an up and down motion, and then take size 15 and push it to length, and then take size 25 and push it to length, and file up and down, up and down. Every time we had a curved canal, well, you know how frustrating that was, because we had the risk of canal ledging, canal transportation, canal blockade, and apical zips. And you see on the screen here, what we have are magnification of resin blocks. What you see in black would be the original shape of the canal, and in white the superimposition after shaping this canal up to size 20 only. Imagine if we use a 25 or 30. This is only size 20 stainless steel hand filing. And you see how we can ledge the canal, you see how we can create apical zips. These pictures were given to me by Elio Beruti, as you can see on this screen. And let me explain to you how this happens. This happens when you put a file in a curve. We were all told that you take a curve, and then when you pre-curve your file, you can put it in this canal and that will be fine. Well, you know that can be fine only if you don't have to shape. You take a file, you pre-curve it, you put it at length, and then what you have to do is enlarge this canal. And so what you start doing, and that's what we were taught, and you take this file and you start doing up and down movement in the canal. The file will go into the inner wall of the curve. You have creation of a lever effect, and the tip will displace, transport the curve, because you have this big force that is restored by the file. And this is how you end up ledging the canals. This is how you end up making ovalization of the apical foramen. So basically what we have to understand is the most important thing would be the movement of the file. Then of course, if the file is made of stainless steel, if the file is stiff, you will have more problems, and these problems will occur quicker during the preparation than if you have a very flexible file. You can obtain exactly the same ledges using nickel titanium if you work long enough in an up and down motion. So up and down motion is definitely not the best motion to enlarge a canal. The first person who understood this, and we have to really acknowledge this, was Jim Rohn from Oklahoma University. Remember that in 1985 he described the balanced force technique. And he understood these problems perfectly and understood how bad were these up and down movement. So he created this balanced force movement in which you will use your file in a clockwise, counterclockwise movement. No up and down movement at all, just clockwise, counterclockwise. The main difference would be that in this concept, the files are cutting their way while getting into the canal. In the way we were taught before, we used to take the file as deep as possible, and we used to enlarge the canals by filing the walls up and down. In the balanced force concept, you use a file that is bigger than the canal, and the file is cutting its way while getting in. The file had a special design. It had a triangular cross-section because it allows the file to be with less metal mass, so it made it more flexible. The file was grinded instead of being twisted. just one thing, I don't know if I told you, it was a stainless steel file at that time. And this stainless steel file was triangular, it was grinded, and especially the most interesting thing, it had the tip of this file was modified. And he was also, Jim Rohn was also the first one to understand that the most aggressive part of the file was not really the tip, but what is called the transition angle, which is where the tip of the file meets with the first flute. And this connection here between the tip and the first flute is very aggressive, and it was completely taken out. So it will make these files with a small tip that is like a bullet shape, and the tip of the file is completely guiding the file in the canal. And the movement is only clockwise, counterclockwise movement. The file is cutting its way down. The tip of the file is non-cutting and guiding the file in the canal. Many studies were published at that time, and they all compared the use of the same files, flex R files, up and down movement, or balanced force. Just by modifying the movement using the same file, you will find that when you use the balanced force concept, you will have no transportation whatsoever in the canal, and the curvature will still and keep its original position. So again, the movement is very interesting. So it's no wonder why when we had the first nickel titanium on the market, it came into a rotary movement because it mimics a little bit this movement. And at the same time, we had the combination of a new alloy that was much more flexible, which was nickel titanium. At the same time also, you know that you can make from one file to another, you can make one file more flexible than the other, just with the same alloy, just by modifying the cross-section, for example, or by just modifying the helix angle and the pitch flute. We can also make the files today more flexible, more resistant, just by modifying the alloy by heat treatment, and I will discuss about this a little bit later. Today we have plenty of files on the market. All the manufacturers want their own files. We don't have the time to go into all these different files. I will focus today on two things. The first thing is I will speak about reciprocation, the movement by itself, how interesting this movement is, and why this movement is really, I will say, like a quantum leap today. And I'm really confident that reciprocation will evolve, and most of the files will be reciprocating in a few years from now. And the second thing then, I will address Wave.One and Wave.One Gold. When we go back into reciprocation, reciprocation is not a new movement. The only thing is, when nickel titanium files went out on the market, it was much more easy for manufacturers to go into continuous rotation because everybody knew rotation. It was much more difficult to have electronic chips into motors to calculate reciprocation. But the first publication about reciprocation was done by Augusto Malentacca in Italy in the Italian Analytic Journal. And at that time, Augusto was discussing reciprocation and showing that reciprocation is safer basically because you will have longer resistance to cyclic fatigue. And we will address that in a minute. At that time, the idea was just to use the same sequences of file just by modifying the movement. At that time, we were not speaking yet about single file techniques. We were just using the same sequence. If you were used to use Profile, ProTaper, RevoS, whatever, it was just, instead of using rotation, just use reciprocation because it would be safer. And we'll see what the literature says about that. But at that time, most manufacturers didn't go into it because the idea was if we just modify the movement and we tell the practitioners you just have to buy a new motor, not a lot of practitioners would have bought these motors. So manufacturers didn't go into reciprocation. What made it most interesting is when we had a combination between reciprocation and shorter sequences. The first person who talked about this was Ghassan Yared, and we have to give him credit for that. He was not the first one to speak about reciprocation, but he was the first one to say we can reduce the number of files by using reciprocation. And that's the most interesting thing. And he published this paper in International Analytic Journal in 2008 describing how this new idea of shaping canals using only one nickel titanium file in reciprocation instead of using a sequence in rotation. And at that time, he was he's a user of ProTaper, and he saw that when he was using his sequence of ProTaper that most of you know, S1, S2, F1, F2, and then you get with the F2 in most of the major roots of molars, in premolars in which you have two roots with two canals. That was the final file he used to use. After, what you do is you gauge your canal, and if the foramen is larger, you would go to a larger file. But in 80% of the cases, that was the file he was using as a final file to shape these small roots. And so the idea was, instead of using these 4 files in rotary motion, we could just take one file, the finishing file 2. At that time, he used the Technica ATR motor. It was the only available motor on the market with which you could really adjust different angles of reciprocation. He determined that the counterclockwise rotation should be 90, the clockwise rotation should be 160, and these angles are specific to finishing file 2 of ProTaper. We were able to shape canals just using finishing file 2 as one single file. So again, instead of using S1, S2, F1, F2 to get to 25-8% taper using rotation, we could take advantage of the reciprocation movement to use only one file, the finishing file 2, to shape our canals to 25-8%. Then, should we need to enlarge a little bit more, we can enlarge a bit more with a larger file. But instead of 4 files in rotation, we used one file in reciprocation. So that was the idea, that was the launch of the idea. And then we had to wait for a few years between 2008, 2007 and 2011 before we had Wave.One and Reciproc. Now, before addressing the files, let me address the movement, how interesting the movement is. Let's see what we can look at when we discuss the movement and when we discuss files. The first thing about reciprocation. Is it eliminates virtually all screwing effect that you can have with rotary files. When you use certain rotary files, well, you know that it's like they look like a screw, and you rotate in the direction of the screw, and then you have a risk of this file pulling you down. It doesn't happen every time, but it is one of the risks in with different instruments and depending on the canal shapes. So instead of having a rotation in which you have a risk of this instrument pulling you in, when you have a reciprocation movement, and it is important to understand it's an asymmetrical rotation movement, alternate movement, this movement will take you in and the motor will go back and move you in again and go back and move you in again and go back, so it will eliminate the screw-in effect. Well, basically you don't need to have much studies to understand this. The most interesting thing also is, and this is already something that Augusto Alentaka had talked about, was that you have less cyclic fatigue. One more thing is you have less risk of fracture by torsional load. I think that these two things are very, very important, and that's the main issue when we discuss about reciprocation. When we discuss with most colleagues and we talk to them, and we tell them why you're not using nickel titanium if they're not nickel titanium users, or if we discuss with them and we ask them what are the problems that you face with nickel titanium, most of their fears focus on fracture, safety. So basically, whatever we can do to make it safer fracture-wise is something we would welcome. And if we take a look at most of the studies, and we'll take a look at these, you will see that from the cyclic fatigue point of view, reciprocation is much safer than rotation. The second thing, when we discuss about fracture by torsional load, reciprocation is also much safer than rotation, and we can address that in at the end. So that's from the safety point of view. Now we have to take a look at different other things about the movement. And we have to see if this movement will induce canal transportation. You will see that from the literature and all the studies that were published in the past 4 years now, that you almost have no canal transportation. And every time you have comparison between what is called the gold standard, which is rotation, to reciprocation, Reciprocation will perform at least as good or better from the side of canal transportation. Then we had different issues about debris extrusion, and we'll address that, but you will see in most of the studies it is either identical or less than continuous rotation. The issue of microcracks also I will address, and also the cleaning, and I'm giving you here a summary of what we can find in literature. All of the studies, or most of them, will show that you have a cleaning that is identical versus rotation in sequence or not. So let's go and see most of these points. The first thing I'm going to talk about is the cyclic fatigue. If we discuss about cyclic fatigue, well, you know that cyclic fatigue is all the stresses that accumulate in an instrument every time you use the instrument. And this accumulation of cyclic fatigue in an instrument will depend on the shape of the instrument. What I mean by shape of the instrument is the diameter, the taper, and the cross-section. And you know that the bigger the diameter, the bigger the taper, the bigger the cross-section, the more cyclic fatigue the file will accumulate. So cyclic fatigue is basically something that will break your file whenever you have enough stress in the file, and it happens without any sign of permanent deformation. That's why it's quite vicious. Another thing that will influence cyclic fatigue is the metallurgy of the file. And we know that, for example, if you take nickel titanium, if you take a nickel titanium and you have a heat treatment of nickel titanium, you can increase resistance to cyclic fatigue. So the metallurgy also has a role to play. Anatomy, canal curvature. If you have a long and gradual curvature, you will accumulate less cyclic fatigue than if you have an apical hook. Whenever you have an abrupt curvature, like an apical hook, your file will accumulate a lot of cyclic fatigue. So basically, when you think about it, if you have a big file with a big taper, a big diameter, and you go into an apical hook, that would be the best invitation to break by cyclic fatigue. The smaller the file, the less tapered the file, and this file will last longer in cyclic fatigue. Now, we always have to find a balance between how big the file should be to give us a good shape in the canal and a good shape to allow irrigation in and to keep that file as safe as possible. And last thing, and very interesting thing, the instrument dynamics, how you use the instrument in the canal, either by rotation or reciprocation, plays an important role, very important role in cyclic fatigue accumulation in the instrument. And when you take a look at what manufacturers have tried to do to increase cyclic fatigue resistance, I'm going to discuss metallurgy, for example, mainly. When you take a look, you see that you have ion implantation. It didn't gain wide acceptance because it is very expensive, very difficult to perform. Electrochemical polishing, and for example, FKG use electrochemical polishing on their files, race, for example. Physical vapor deposition, that is used by Comet on their alpha kite files. And most of the manufacturers will use heat treatment, Densply with the M wire, the gold wire, Cybronando, and Coltine are using heat treatment on their files to make it more resistant to cyclic fatigue, more resistant to corrosion, and sometimes one of the claims is it's also more flexible. So we know that if we use heat treatment, for example, if we replace normal nickel titanium by M wire, in fact, we don't replace it, it's just the same raw nickel titanium, and this wire is subjected to a heat treatment of heating and cooling with different cycles. You get what is called an M wire, and it has been shown to be more resistant to cyclic fatigue. Today, we are discussing Wave.One Gold, and Wave.One Gold also is another type of heat treatment, and also it is an improvement of M wire, and I'll discuss about this later. You will see that it makes the file more resistant, more flexible, and also with almost no restoring force on the file, which is very interesting from canal transportation point of view. If we have to go through literature today to discuss what is happening and about the studies on cyclic fatigue, We're not going into all the literature because most of the studies today, and all of them, in fact, not most of them, all of them will show for every single instrument, whatever the instrument, regardless of the manufacturer, regardless of the brand, whatever the instrument, whenever you take this instrument and you reciprocate, this instrument will last longer than if you rotate. It is much safer. Just to give you an example, that is one of the first studies to be published by Gustavo de Dias about reciprocation versus continuous rotation. At that time, you see, it's 2010, we didn't have yet Wave.One and reciproc on the market. We only had the publication of Ghassan Yared about finishing file 2. So basically what was done in this study, and you see the model, the file is into a tube. Remember, when we do the cyclic fatigue testing, the file is never blocked. The file is rotating freely. It's just the number of rotation or reciprocation before failure with the file into the curve. So the only stress on the file is the curve. And you can have different levels of curves. You can have different angles of curves to see how the file reacts to this different level of curves. And what you can see in this study here, that if you rotate the file at 400 RPM, it will break in less than 30 seconds. If you rotate the finishing file 2 at 250 RPM, it will last up to 50 seconds. If you reciprocate the finishing file 2, you go up to 100 seconds, so almost at least 100% more. So you can see here that reciprocation is much safer in terms of cyclic fatigue than rotation. And if you take a look at all the studies that were published in the past 3-4 years, you will see that all of them, and I'm giving you all these publications, you can go and take a look, they are available. You will see that all of them show the same thing, and all of them will show regardless of the file. You see that you have these studies by Gambarini, and I say hello to Gianluca here. Gianluca worked on the development of Twisted File, great instrument. They have compared Twisted File in rotation, in reciprocation, and they have found that if you go in reciprocation, Twisted File lives longer. And again, whatever the file, here again, this study by Castello Scriva, ProTaper Wave.One Twisted File, you go reciprocation, it lives longer. Whatever the file, when you go reciprocation, it lives longer. One of the latest studies that were published, again, take a look at this one, 2013, between K3, K3XF and Twisted File, continuous rotation, reciprocation. When you go and you take a look at the mean life, just for example, for the K3, the first line, K3 in continuous rotation, mean life 17.4, K3 in rotation, fifth line 51.3. And this is exactly what you will find, whatever the file. And so you see also, just to pinpoint the fact that it is not the fact that it is Dentsply, it is MyFair, it is reciproc, it is whatever the file. You go in reciprocation, they live longer. The latest publication on this is still online, compared M2 and race. Both of these files are not meant in the beginning to go into reciprocation, rotation files, sequence rotation files. When you take a look here, you see two things. And I wanted to talk about this study just to explain a couple of things. The first thing you see, if you compare for M2 and for race, so for every single instrument, you take M2. You take a look at this graph, you will see on this table, you see that M2, the standard time, if you go the time and the standard deviation, if you go continuous rotation, it's almost 280. If you go reciprocation, it's almost 815. If you go with race and you compare in continuous rotation, 173, reciprocation, 337. So for every file, you will see that if you go reciprocation, they live longer. Now, if you compare M2 to race, you will see that M2, either in continuous rotation or reciprocation, has longer cyclic fatigue life. How come? Remember, race is electropolished. And then the claim is when the file is electropolished, it will last longer, which is true. If you compare race that is non-electropolished to race electropolished, it will last longer. But remember that electropolishing is not the only thing that will play a role on cyclic fatigue. Important thing also is the cross-section. And the main difference between race and M2 is the cross-section. So the cross-section also plays a role. And you will see here that the fact that the cross-section is smaller is more important even than electropolishing. And of course, if you take M2 and if you electropolish M2, probably if you compare M2 non-electropolished to M2 electropolished, when it's electropolished, it will also have a longer life. So treatment of the alloy is not the only thing. What is also important is the design of the file, the cross-section, and all other features. Okay, let's move. Oh, yeah, I just wanted to show you also this file, this small video, also another model of cyclic fatigue, and you see it was given to me by my friend Jose Aranguren, who is also going to lecture on this on the Endomasters, and I'm really happy for my friend to be here also. And this is a model in which you see that you have a tube at 90-degree curve, another at 60-degree curve, and a third one at 45-degree curve. And well, if you compare in this case Pro-Taper versus Wave.One, you will see that you have comparison at 45 degrees between Pro-Taper and Wave.One, comparison at 60 degrees curve between Pro-Taper and Wave.One, and comparison at 90 degree between Pro-Taper and Wave.One. First thing you see that whenever you reciprocate, you live longer. It's not only reciprocation, because at the same time, don't forget that Pro-Taper has a different alloy, because Pro-Taper is normal, I would say conventional nickel titanium. Wave.One is nickel titanium M wire, so that will play a role. Second thing, Pro-Taper and Wave.One don't have the same cross-section, and that will also play a role. And also the movement will play a role. So the combination of the alloy, the cross-section, and the movement makes it that you go almost 20 seconds with the Pro-Taper, and you go 133 seconds with the Wave.One. Now what you can see on the right hand of the graph with the 90-degree curve, you see that with Pro-Taper 0.06 and with Wave.One you're 0.88. And you see that both times are smaller than the second. It means that even if you have rotation, reciprocation, it means that clinically, whenever you have an apical hook that gets closer between 60 and 90 degrees, you should never use mechanical files. Neither rotation nor reciprocation. No mechanical files. You shape by hand, and usually what I do is I take any nickel titanium file and I reciprocate or rotate by hand, because you control the pressure, you control the number of movements you do, and you are safer from this side. So I wanted to show you this graph because it is important to understand that the movement plays a role, the alloy plays a role, the cross-section plays a role, but the anatomy is still something we should always take a good look at. If you have an apical hook, you are in danger and you should not use any mechanical files. That was from the point of view of the cyclic fatigue. Now, a very interesting article I wanted to show you also. It was an online article that was published in still online for the time being, the time I speak to you. Maybe by the time you'll have it, this lecture goes on internet, it will be published on paper. That was a clinical study on cases, clinical cases, and that's what is interesting to us. Basically, that was done with Wave.One, and you had, like you can see, 2,215 canal preparations on 711 teeth. The fracture rate, basically 3 files fractured. 2 Wave.One small, the 2106 taper, and 1 Wave.One primary, which is the 25.8% taper. The overall fracture rate is 0.31%. If you take a look anywhere in the literature concerning continuous rotation, the fracture rate, it will go somewhere between 3-4% up to 8-10% of fracture rate. Frankly, at 10% rotation, that is huge. Probably there's a way the instruments are used that is not proper. And you can't accept something like 10%. But basically, in most of the articles, let's say the average of breaking rotary files goes between 3 to 4%. So when you see here with the reciprocation movement and a single file technique, we are 10 times lower than the published average in rotation. 10 times safer in reciprocation. And that again is a clinical studies on patient. Now let's go to the second point we have to discuss. I will go faster on these ones. We need to compare the canal transportation and the canal shaped after shaping, either with the rotation or by reciprocation. And you can compare depending on the studies, and you have to take a good look at the material and methods of these studies. And you have to see if we are comparing a sequence in rotation versus a sequence in reciprocation, or if we are comparing a sequence in rotation versus a single file in reciprocation. And then you see that this can be an influence on the results. Anyway, in this case, it was a full sequence in rotation versus one file in reciprocation. At that time, it was still the finishing file 2. It was one of the first studies published comparing reciprocation and rotation in terms of canal transportation. It was done in Zurich University by Frank Paquet and Matthias Zender and their team. And well, again, I salute them here. I hope they're fine. And basically, they have found doing the micro CTs before and after and superimposing with the three-dimensional images of the canals that you didn't have more canal transportation using one single file versus multiple file in rotation. And the results show that we had an excellent canal preparation. And if you go through literature in the past 4 years, you will have exactly the same results over and over again with the studies of you done. These studies were done in Korea, different studies with Franco. I think this study was done with Flexmaster, the study of Stern, and the study of Elio Beruti and his team down in Torino. And you will see that all these studies comparing continuous rotation to reciprocation will show that reciprocation performs at least as good as rotation, and in many of the studies better than rotation in terms of root canal anatomy. Now, something that was a matter of debate was debris extrusion, and let me elaborate on this. Well, just to summarize, let me tell you that there is only today, from all the studies that were published, only one study that shows that you have more debris extrusion using reciprocation, and I'll elaborate on this. The first study comparing reciprocation to rotation was published by Gustavo de Deis in Oral Surgery, and you can read here very simply the summary and the conclusion. They didn't find any difference in the amount of extruded debris between finishing file 2 used in reciprocation versus a full sequence in rotation using ProTaper. And there we had a second study published by the study of Berkline and Schaefer, and this study showed, and at least from the protocol of the study, the results were you had more debris extrusion using reciprocation. Now, I would like to elaborate on this study. Not that it is a bad study, it's just that if you elaborate and take a look at the material and methods, you understand why we have these differences. The first thing is, remember that in this study, and let's focus on the second table here. I'm not really interested in preparation time at that point, even though it can be something interesting. But let's talk about debris extrusion. First, what you can see is all the techniques extrude debris. ProTaper, M2, Wave.One reciproc. Now, can we from this protocol conclude that reciprocation is extruding more debris? I'm sorry to say that we can't, for different reasons. The first reason is when you use ProTaper and M2, you are using a sequence of file. So you go with multiple files, at least 4 or 5 files in rotation. And you compare this to single files in reciprocation. So if you have more debris extrusion in one technique or the other, there is no way you can say if the problem is related to the movement or to the fact that we have used a sequence of file versus one file. What I mean by this, that if you want to see the influence of reciprocation as a movement, you have to compare a sequence of file in rotation versus a sequence of files in reciprocation, and then the only different parameters between them would be the movement, and then you will know if the movement is inducing more debris extrusion. So that's one of the first bias in the conclusions. The second issue is, when you take a look at the apical diameters of these files, you'll see that the Pro taper is a 40-06 taper. The M2 apical diameter is a 44% taper. The Wave.One is a 48% taper. So if we stop just here and we compare M2 to Wave.One, we are comparing not only two files, we are comparing also two different apical tapers. The M2 is a 44% taper compared to Wave.One 48% taper. So how do we know if the extrusion of debris is because of the files by themselves, because of the movement by itself, or because of the double taper that we have in the Wave.One? So I'm not saying this study is bad, I'm saying that just what we can say is, and this is why I think that it can be misleading, we can't say that reciprocation is extruding more debris than the rotation, because the way the study was built cannot enable us to conclude this. Okay, now if we go to other studies that were published, most of the other studies that were published are showing exactly the opposite. For example, this one, if you take a look about extruded bacteria beyond the foramen, you will see that in this case we have less debris and less bacteria extrusion with Wave.One and reciproc versus multi-file race technique. Just one thing to tell you about this. Probably one of the reasons why we have more debris extrusion using race, it's because when you use race, every single file is used to length. Again, please, I'm not saying any of the files are bad. All the files are good. We have just to keep in mind that these studies are made on extracted teeth, and these studies are very difficult to transport to clinics. But anyway, because they are used from time to time, and they are used sometimes in lectures, and people will talk to you about it, and they will just show you the conclusions, you always have to take a look at the material and methods, and sometimes you will see that the material and methods will show some kind of bias, and sometimes the conclusions are not that fair at all. In this case, remember that when you take the multi-file race, every file is going to length. So, of course, you will use the pre-race in the coronal area, but then you will take the 15 to length, followed by the 20 to length, followed by the 25 to length. And then every single file going to length will push a little bit of debris. While when you use a file and you use in the coronal area first and you irrigate, then you go deeper and you irrigate, and then you go deeper and you irrigate, then the tendency of this file to extrude debris will be limited to the final millimeters of the canal, because you have enlarged the coronal part and you have cleaned all the coronal part before getting your file to length, which is not the case with the files that you get one after the other to length. So anyway, if you take a look today, you'll see that in most of these studies, when you compare the rotation to reciprocation or to the SAF system, most of the all of the files, all of the systems will produce some debris extrusion. But what we have to keep in mind is reciprocation do not push more debris or more bacteria apically than rotation. And you see also, this is one of the latest studies that were published about this. You see that this one is comparing Revo-S, which is a simplified technique in rotation, to the reciprocating file in rotation. Even though Revo-S is at the 25.6%, reciproc is at 25.8% in reciprocation. Well, probably because of the cross-section, you have less debris extrusion. Probably also because of the movement, you have less debris extrusion than a rotary movement. Now let's go and discuss cracks, which is the fourth or the fifth point. I don't remember. It's not a problem. Let's go on cracks. Again, when you take a look at cracks, it's like everybody today is discovering cracks because of reciprocation. but cracks have been known for a long time. One of the first studies that was published on cracks was published at a time in which we didn't speak about reciprocation yet. It's a Japanese study by Adorno and his collaborators, and let me just elaborate a little bit and show you what the material and method looks like. They used mandibular incisors. They tested profile, K3 and endowave. They had the intelligence to use the same apical diameter just to be able to compare apples to apples. And they tested the files, and they tested either the canal length at -1, at which they stopped the preparation, or at canal length plus 1 millimeter. So extruding the files out by 1 millimeter from the outer surface of these mandibular incisors. What did they find? And just remember, all these files are used in continuous rotation. They found that first, all system caused little micro cracks. Second, that you had less cracks if you were working short. And third, and very important, they found that you had more cracks when you enlarged with bigger diameters apically. So just keep this in mind, because the same people who are telling you don't use reciprocation because you create cracks, the same people are telling you you should enlarge at least to 35 or 40 in rotation. Well, if we want to stick to literature, we should keep in mind that the more you enlarge apically, the more you create cracks. Now, let's go to the study of Berkline and Schaefer. Again, the study of Berkline, and showed that same thing, you had more cracks using continuous reciprocation instead of continuous rotation. Again, if you want induce to talk to people and tell them, don't use reciprocation, you can just take the conclusion of the study and say, Berkline and his team has made a study and they have shown that you have more cracks using reciprocation, so don't use reciprocation. Now, if you go into the details of material and methods, and that's why I'm showing you this, take a look. First thing, they have used mandibular incisors. So these are the smallest teeth in your mouth. The second thing, they compared M2 Pro Taper Wave.One reciproc, and take a look at the apical diameters. They have compared first a sequence of file using M2, sequence of file using Pro Taper rotary, to reciproc in reciprocation, Wave.One in reciprocation. M2 is a 44% taper, Wave.One is a 48% taper. Just by taking a look at this protocol. If you are using these files on mandibular incisors, and you are using a 44% taper and comparing this to a 48% taper, what do you expect the results to be? Well, basically, you know that using an 8% taper in a mandibular incisor, you will have more cracks. Is this study worthless? It is not worthless. This study shows one thing. It tells you if you have mandibular incisors, don't use 48% taper. Can we draw conclusions on reciprocation and say that reciprocation as a movement will create more cracks? Sorry to say, we can't. So if it's used in all these marketing brochures of competitors or by different lecturers or advocates saying, don't use reciprocation, this study has shown that you have more cracks with reciprocation. Take a look at the material and methods. It doesn't show this. It just shows that mandibular incisors, if you use 48% taper, you will have more cracks than if you use a 44% taper, and you can expect this. Now, if you take a look at all the other studies about micro cracks, well, they will show the opposite. One shape in rotation, single file technique, 25.6% compared to reciproc, 25.8% in reciprocation, less cracks with reciproc, which is a single file in reciprocation compared to a single file in rotation. Even though we have 2% more taper, we have less cracks. If you take another study, that study was done on mesial canals of mandibular molars. Same thing. you see that we have in this study what was compared was night-eye hand files, 2% taper, up and down motion, pro-taper hand files, pro-taper rotary files, and Wave.One reciprocating files. And you will see that if you take a look in the apical sections, middle sections, coronal sections, it's almost comparable between pro-taper hand files and reciprocating Wave.One. Pro-taper rotary will induce probably a little bit more cracks because you go rotary with a motor and you have big files and you have more stress on the roots. But I'll discuss about this in a minute. One more study, that study is still also online. When you compare Wave.One finishing, Wave.One in reciprocation with finishing file 2 pro-taper in reciprocation versus a full sequence of pro-taper, you have more cracks using a full sequence in pro-taper. And so if we want to summarize the literature about micro cracks, you will find that except of the study of Berkland and Schaefer, in which they have shown on mandibular incisors that you shouldn't use a 48% taper, which anyway I never use unless I have a very big apex and a very absorbed tooth. All of the other studies, including this one by Dedeus, have shown that you don't have more cracks using reciprocation than if you use rotation. What else can we say about all this? Well, last thing, cleaning and disinfection. And this is the last thing I'm going to speak about literature before we go into the files by themselves. Again, all these studies, when you compare them all together, as long as the final shape of the canal is the same, if you obtain this final shape using one file in reciprocation, if you obtain this final shape using several files in reciprocation or rotation, as long as the final shape is the same and you are able to get your volume of irrigation down, you will see that all these studies have shown that you don't have less cleaning using reciprocation and single file technique. You don't have less cleaning than if you are using multi-files in rotation. So reciprocation is allowing you to clean the canals at least as good as rotation when we take a look at most of the studies that are published. Now let's go to the files and to reciprocating files. You know that in February 2011 we had the introduction on the market of Wave.One made by MyFair and Reciproc that was made by VDW. Both single file techniques. I will speak about Wave.One and then the evolution, which is Wave.One Gold, and somebody else in the Endomasters, I think Gustavo Dedeus, will discuss and explain to you Reciproc. So we have understood that we have alternate unequal reciprocation movement. That's the first thing. The second thing, we consider that you need your file to be bigger than the canal because the file is cutting its way down. So when you take a look at this, what we call the primary file, which is really the workhorse of the system, this file will be used in more than 80% of the cases. And in many of these cases, it will be the only file that is necessary to shape the entire canal. This file is a 25/8% taper and it features a reverse taper. And this file will allow to work basically on mesoroots of molars, on premolars with 2 canals, 2 roots or 3 canals, distal root of upper molars, distal roots of lower molars if you have 2 canals or if you have restricted canals, palatal roots if you have restricted canals. Now, of course, if you take this one and you go into a canal and you find that the primary is not cutting enough while getting in and you don't have resistance, it means that the canal is much larger than the file and you have to take a bigger file. Now, we also have a small file, which is a 21/6%. Many people like this file to work on MB2s, for example, on upper molars whenever you had restricted canals. In my opinion, this file, I use this file just to bridge preparations. I don't use it as a first file. What I mean by this is I would take my primary, and I'll discuss with you, I will just scout the canal, establish glide path, and secure glide path. And after securing glide path, I will always start with the primary. Now, if the primary has some trouble getting in, then I will shift to the 21, the small. I will open the pathway with the 21, and then I will move back to 25. I almost never finish my preparation with 21. I will always like to take them up at least to 25.8%. And then what we have is a bigger file, which is the big Wave.One 48% taper. Remember this one that was used in incisors, mandibular incisors, in these studies about cracks. This one is made for big canals. Allow me just to speak just a minute about the canal concepts. If you believe that you need to enlarge apically to size 35 or 40 to have canals clean, this system, Wave.One, is not for you, because the Wave.One system is based on creation of apical tapers. Okay, so if you are part of the endodontic community that thinks that we need to over-enlarge apically to make it cleaner, you shouldn't use 48%. You should use a file which is 35 or 40 in diameter, but with much smaller taper. What I mean by this is that file, the 48%, is meant to prepare large canals. It is not meant to prepare small canals to big tapers or to big diameters, okay? And as you know, the Wave.One file, one of the novelties of the Wave.One also was that it was made of M-wire. And as I told you, this M-wire, usually you have the nickel titanium, conventional nickel titanium, and before machining, before grinding of the wires, these wires are subjected to heat treatment, cooling and heating, cooling and heating, cooling and heating under stress, and it gives the file, it gives the alloy some specificities, and it makes it more resistant to cyclic fatigue and more flexible. So these are the basic files. They come in blisters, they come in already sterilized, they are meant to be single use. You take the file, you use it for one patient. It's single patient use, it's not single canal use, it's single patient use. You can shape 1, 2, 3, 4, 5 canals with the same session, within the same patient, with the same file. You know that these files then are single use. This is the philosophy of the file. Basically, if you take a look at the sequence I use, and that I will show you a little bit later, I scout the canals using a stainless steel hand file, size 8, size 10. I will establish my glide path. Then I will secure my glide path using path files, rotary nickel titanium, either path files or pro gliders. And then I will shape. And then I start shaping with my Wave.One primary, coronally first, 1, 2, 3 strokes, take the file out, clean the debris, irrigate, recapitulate with your stainless steel hand file, and move deeper. One of the things you have to understand about reciprocation and single file techniques is that you are using one file with a big taper to shape your canal. You are not increasing the diameter of the canal gradually using multiple files. I mean by that your file is taking some loads, and also it is loading debris in the flutes very quickly. So what you have to do is 1, 2, 3 maximum, take it out, clean the flutes from the debris, and then move deeper. If you don't clean the flutes, if you don't irrigate, you will have a lot of accumulation of debris. Your file will be less efficient, it will cut less, and then you will start pushing more debris apically. These files are single files. They have to be used differently than if you are using multiple files in rotation. And just to show you a couple of cases, because I want to move to Wave.One Gold, these two premolars done in the same session, basically less than an hour. You have one anesthesia, one rubber dam, 2 access cavities, and these files are shaped using one and the same Wave.One primary. And then filling is done with a warm vertical compaction. Just to go on one more case, because many people said 25 is not enough. Well, frankly, we never said you have to stop at 25. What we are saying is, instead of using 4 or 5 files to get to 25, you are using only 1 file to get to 25. Now if the apical diameter requests to use a larger file, or if you wish to use a larger file, well, you're free to do so. If you take a look at this case, you see that you have a lesion on the medial root of this molar. My sequence will always be the same. I will use first my stainless steel file to scout the canal, establish working length. I will use my path files to secure my glide path. You know that the second path file, the white one, is a diameter 16. And then I will use my Wave.One primary. Now, if you get to length and you realize that the apical diameter is larger than 25, any file larger than 25 will cut apically and will be satisfactory. What I used to do in my practice is I use the finishing file 3 Pro Taper hand just to go there because I needed to enlarge apically a little bit more. So we adjust to the anatomy. Instead of using 4 files to get to 25, we use the 25. If apically it is satisfactory, we're done, and then we irrigate. If apically the diameter is larger than 25, we use larger files. And whatever file you would like to use will be your own choice. And this is the follow-up, and this is the healing of that case. Now let's go to the evolution of Wave.One Gold. Well, you know, we have been working in the past 2.5 years to make Wave.One evolve. It was quite difficult to convince MyFair to evolve with Wave.One because, well, the file works pretty good. And it's very difficult to say to a manufacturer, you know, the file works good and we need to improve it. And then they will say, why do you need to improve it? Well, because when you work with a file on a daily basis, because when you lecture and you go doing hands-on and you're in contact with different colleagues, you start seeing that sometimes you have a little bit of gaps in the system, or you can see that you can improve a system. And every system can be improved. And for the past 2.5 years, with my friends here, Cliff Ruddle, Julian Weber, and Sergio Cutler, we have been working with the MyFair team to evolve with Wave.One and to give you Wave.One Gold. It is based on the same central philosophy of single file, single use technique, single patient use technique. And the file was modified. And as you see by the name is Wave.One Gold. It's not MY anymore. It's another heat treatment that will be different on this file and will give it different characteristics. So Wave.One Gold today, I'll describe these files to you. As I told you, it will be available starting IDS. Some of you people might have heard of these files before. We're starting to talk about it just to introduce it in different lectures. But the official launch would be IDS in Köln this year, so in a couple of months. As you can see immediately, we have 4 files, so we have an additional file, and I'll discuss all this with you and show you what the diameters and tapers are. Let's go back to the origin. The origin is we have Wave.One, primary, small, and large. Well, the primary will stay the primary, and we still have a primary file which is a 25, but at this time it's a 25.7% instead of 8%. We reduced a little bit the apical taper. We reduced also the coronal taper and the coronal diameter, and I'll show you this in a minute by comparing Wave.One Gold to Wave.One. We also have a small one. This one again will be used as a bridge in very small and restricted canal. Also, I'm going to tell you that would be, you know, today this new fashion about minimal invasive endodontics. For those of you who are the lovers of this technique, that would be the ideal file for you. If you wish not to open more than 20 at the apex, it would be at 27%. Very little preparation, as long, of course, as you are able to get all this canal cleaned without enlarging more. What we have also is we have replaced the 48% by a 45.5%. And because we saw with the first Wave.One that we have a gap in the middle between the 25 and the 40, then we have an additional file for you. This file is a 35.6%. So for those of you who wish to enlarge apically a little bit more because they feel more confident with a more open and enlarged apex, if you have your primary to length, you get your 25.7% to length, then very easily in most of the curves, you can get your 35.6% to this length and enlarge more. I'm not saying this is what I do. I'm saying for those of you who wish to open more, you have the 35.6% available. I'm saying also that if you get your primary to length and then your apical diameter is larger than 25 and you need to enlarge more, then you have your 35. And 45.5% will be for big canals if you wish to shape them using reciprocation. So we have more files allowing to cover even more clinical cases. Let's take a look at the characteristics. This drawing here was given to me by my friend Sergio Cutler from Fort Lauderdale and illustrates a little bit how Wave.One Gold is made. Well, remember I told you with M-wire, you took the wire before grinding and then it was subjected to the heat treatment. With Wave.One Gold, the files are machined first in the conventional Night-Eye and they are heat treated after machining. Then after you put the handle and you put the stop. This is just the way it is done. And it's also a heat treatment. And this heat treatment of gold wire, if you compare it to M-wire, first it gives an increased flexibility. The second thing that is very interesting is that it has almost no restoring force. And we'll see in a minute what restoring force is. And also, very interestingly, it has an increased resistance to cyclic fatigue. Now, of course, everything has to be comparable. The cross-section is different, and we'll discuss this also in a minute. This is a Wave.One, traditional primary Wave.One with M-wire. You see that if you bend the file, you need a little bit of force to bend it, and it will come back to its original position. This is the gold primary. If you bend it, you need much less force to bend it, and you see that the file doesn't go back to its original shape. What is the benefit of this? When you take a file into a curve, this file has a tendency to straighten. It wants to go back to its original shape. This is what we call the restoring force. If you are in the curve and the file has a big restoring force, it will cut dentine from the outer surface of the curve, and then you will have canal transportation. Whenever you have a file that will accommodate the curve and with no restoring force, it will follow perfectly the curvature and you won't have canal transportation. That's one of the really good features of gold. Now, another thing about Wave.One Gold is that the cross-section is different than Wave.One. It has a cross-section that looks like a parallelogram. This is close to the tip. This is closer to the handle. This cross-section, I wouldn't say it's a swagger file, but basically the way the cross-section is built, if we consider that we have a round canal, and you know that sometimes the canal is not round, the canal will be oval, and sometimes we need to brush against the walls just to clean a little bit this oval. But basically, if we consider a round canal, you will see on these drawings that this file will not contact all the dentine walls with the four angles at the same time. By not contacting the four angles at the same time, you have less stress on the file, you have more place for debris removal, you will auger more debris, and this file will give you better results in terms of stress, in terms of shaping. If we consider then the cross sections of Wave.One that you see here, that is the original Wave.One, to the cross section of the Wave.One Gold, you see that we have the same parallelogram cross section on the Wave.One Gold. Now, if we compare the primaries, on the apical diameter and taper, we had a 25.8% with Wave.One, and now we have 25.7% with Wave.One Gold. But also what we have is we have less tapers coronally. So at the D16 with Wave.One, we had 1.2 millimeters, while we will end up with 1.135 when we are with the Wave.One Gold. So you're cutting less dentine coronally, and you will have more conservation of canal dentine coronally. Of course, this is if you don't use any other file coronally. So the file has the same apical diameter, 1% less taper, but coronally you have a reverse taper that is more important, and the coronal diameter of the Wave.One Gold is smaller which makes it, of course, more flexible for different things. It will be more flexible because you have a different cross section. It will be more flexible because you have the gold wire. It is more flexible because you have less taper and less diameter. And if you see here this graph and you compare Wave.One primary M wire with Wave.One gold primary, we are up to more than 80% more flexibility of the Wave.One gold. Again, if we compare cyclic fatigue resistance with the primary, we have almost 50% more cyclic fatigue resistance when we compare Wave.One primary with Wave.One gold primary. And again, it's not only the gold wire, it's always the combination of the alloy, the combination of the cross section, and the combination of diameters and tapers that make the files more safe in this case. We still have the same feature, and we still have a reverse helix on these files. We still have the same angles with these files. When we compare them to Wave.One gold, I mean that you know that Wave.One had a reverse helix. Wave.One gold has the same reverse helix. It means that these files will move apically in the canal when you go counterclockwise, and they will move back counterclockwise. And it means that you can still use the same motors than we had before. They come under sterile blisters. They come either as an assortment, or they come with every single file, every number of file, and they also come in and are available in 21, 25, and 31 millimeter in length. And you still can use the same motors with the same parameters. So the same motors that you have bought, if you have them already to use Wave.One, are still, you can use them to use Wave.One gold, so you don't have to buy a new motor if you already have it. Remember also, these motors allow you to do also rotation if you wish to use Pro Taper. Of course, you should not use Wave.One or Wave.One gold or reciproc in rotation. It will not work. This is not designed to work in rotation. So you still have the same motors, the X Smart, that you can use. And also will be coming soon on the market, the X Smart IQ. This is something really new, probably will be available in June. It's you can pilot your handpiece, which is a cordless handpiece, and this handpiece can be piloted with an iPad on which you can download programs. You can download the programs for every patient, for every treatment. You have all the parameters in the iPad. I'm not going to speak a lot about it because it will only be available in June, but for those who will ask the question, you can have also